going to take you all the way through the fine-tuning of a Llama 2 model. And we'll be doing it in Google Colab, so you should be able to follow along for free. I'll take you right through a basic example, and I'll also show a detailed example if you want to get results with a very small data set. And before that, I'm going to talk a little bit about model size and quantization and why that helps us to use tools like Google Colab. Let's get started. Llama comes in a few sizes. So you'll see there's Llama 2, and it comes in the 7 billion size, 13, and then also comes in 70 billion. And this means this is the number of weights in the model. So you think of the neural net, and that's represented by 70 billion weights in the 70B model. Now, each of those weights typically would be represented, each weight represented by 32 bits. So if you have 8 bits per byte and you have a 70 billion model, that means that you're going to have 70 billion multiplied by 32 bits divided by 8 bits per byte, which is going to be 70 multiplied by 32 divided by 8, which is 70 multiplied by 4. So that means there are going to be about 280 gigabytes of weights. Now, the problem there is if you connect to some kind of a runtime, and I'll show you the first of the notebooks we're going to go through. If you connect to the very first runtime, we'll just allocate some space. Let's take a look at how big the computer is that is allocated to us by Google Colab. Here we're initializing, and I'll put a link to this in the comments. So you can see we currently have, we don't have the GPU started up, but I know when it starts up, because I'm on a free plan here, that it's going to provide 15 gigabytes. So the GPU will be 15 gigabytes in size. And you can see that's just going to be way too small to fit a model that's 280 gigabytes. Now, it's a bit better if we look at the Llama 7B. That's going to be 7 billion multiplied by 32 bits over 8 bits per byte. And that's simply going to be 28 gigabytes. So even Llama 7B would be too big if we represent it in 32 bits. So that's what brings us to quantization, which is a way to shrink the model so that we can fit it into something like Google Colab. And just for reference, when people talk about the most powerful computers like an A100 from NVIDIA, that can come in a 40 gigabyte representation or 80 gigabyte. So you can see that if you were to represent the model in 32 bits, the 70 billion Llama model would still take many of these GPUs. As I said, that's where quantization comes in. So the idea with quantization is instead of using 32 bits to represent weight, you scale it to 4 bits. Now that means that the model is going to be less precise, because if you have 4 bits, that's going to be 2 to the power of 4. So that's going to be 32 discrete values that a variable can take. So it could, for example, be on a scale of 0 to 32, it could be 0, 1, all the way up to 31. Whereas if you have 32-bit representation, then, well, if you're just looking at an integer, that is always going to be positive, for example. I don't even know what 2 to the power of 32 is, but that's going to be a really large number. So you're basically taking a lot of granularity in a large number, and you're going to simplify it down so that there's just like 32 steps. And you're going to have to record a range for when you quantize. So you might take 32 steps going all the way from 0 or minus 1000 to plus 1000 and split that into 32 different steps. And then you can represent the number, which was between minus 1000 and plus 1000. You can now represent it discretely as one of the 32 steps between there. So what this allows us to do, let's say for the 7 billion model, is now to have 7 billion multiplied by 4 bits divided by 8 bits per byte. So now that's going to be 3.5 gigabytes. So the value here is we can now fit this 7 billion model very easily onto a Google Colab notebook. If it has 15 gigabytes, which we'll see in a minute, it's very easily going to fit 3.5. And so that's the idea of quantization. You do have some loss in the accuracy, but actually the loss is maybe not as large as you might think, because some of the weights, it's not that necessary to have very precise values. And in fact, you can even go a step further and decide to quantize or shorten some of the weights and leave other ones that are more important long. And by leaving the most important ones long, you can end up getting a good trade-off and not affecting quality too much. So this brings us on to QLoRa. And the QLoRa is short for quantized LoRa. Okay, so it simply means doing LoRa, which I'll explain in a minute, but quantized. So it means training with quantized weights, 4-bit in this case. And what LoRa means is it's short for low rank. And without getting into too much detail, the idea is that instead of updating all 7 billion weights, we'll just update the most important ones. That's at a very high level what's happening in LoRa. So we're making the training easier because we're representing the numbers with shorter number of bits, 4 instead of 32 or 16. And then also we're not going to update all the weights, we're only going to update some of the weights. And there is a package that's part of Transformers library, which is Hugging Face developed. And there's a part of that library now that's supporting bits and bytes, which is a quantization library supporting LoRa. And just one other note, you'll hear about PEFT. So this is parameter efficient fine tuning, is another way to say we only train some weights. And basically LoRa is a type of PEFT. So that explains QLoRa. Now I'm going to go all the way through. I'll step through every step of the notebook for fine tuning. And then I'll step through a second notebook that's a bit more advanced. Basically, if you're very careful exactly how you fine tune and where you put the emphasis for the model to learn within the prompt, you can train with less data. And that's what I want to talk about in the advanced fine tuning. I'll talk about prompt masking, and I'll talk about the end of sequence token. And that's going to require me to come back and talk about two things. The first will be attention. The second will be loss masking. So I'll come back and talk about those. I think it's more instructive to first go through a simple model. Yes, I am not a robot. Okay, so I'm here on this notebook, and there are going to be a few steps. So we will install the packages. We'll then set up for training. We'll then get some data that we'll use for fine tuning. We'll do some training. We'll do some inference. So we'll run some samples, get some results of output. And then I'll show you how to push that trained model back to the hub. So here we are in the installation. And I've just installed these packages. You can then move forward to loading. So let's get the loading started here. This is going to take probably about a minute. So actually, if you're going to use Llama, this model here, you will need to have the notebook. You will need to sign into Hugging Face Notebook. So I'm going to just get a little snippet of code to do that. This is a snippet to log in. Now you will need to request access to Hugging Face to do this. You could also use Trellis. sharded. So this is a model that's publicly available. You don't need to get access from Meta, and it should allow you to just download without doing the Hugging Face login. Let's just check that this here is the correct one. Yeah. So you could we could just right away do that, but what I'll do is I will log into the notebook instead. So here, I'll add some code and I'll run, and this is going to allow me to log in to Hugging Face. So I'll click on Hugging Face tokens, copy one of my tokens, and log in. Okay, so I've logged in, and now I should be able to run this model without that error because I've been approved by Meta. Just write in here. But you could load a bigger model as well. That would work fine. All right, I'm just going to pause for a moment here while this loads. Should take about another minute. Okay, so this has now been downloaded. Just a few notes. I did have to go back and reinstall. There's a temporary issue. It's August 9th. The latest Transformers library has got a breaking change, so I've fixed it to 4.3.1. But you can see now that the model has been loaded. You can see that this model is about 4.7 gigabytes. In our earlier calculation, I calculated 3.5 back of rule of thumb, back of the envelope, but it's always going to be a little bit higher than what the estimate is. So we have the model loaded, and we can move on to the next step, which is the training setup. So here we set up parameter efficient fine-tuning, which means we'll only update some parameters. Basically, we're setting up the model to only train certain parameters here. Now we're going to get a printout of the number of trainable parameters. This is a function that will print that out. It's not going to print it just yet because first we're going to import configuration. So here, we've run this and this. Yeah, so actually this needs one other fix as well, which I will get from my detailed. Set up LoRa. Okay. So actually to fine-tune Llama, you need to change the target modules. They're just defined differently. And the way you would do that is by running this command here. But the target modules are different than for other models. So I'm going to comment that out. I'm going to put in specific to Llama models. And I'm going to run this. So what's happening now is we're loading the parameter efficient fine-tuning model. with this configuration. And basically, when we say target modules, we're selecting to only update with the fine-tuning certain groups of the weights. So we're not going to update all the weights, we're only going to update certain groups. In fact, we're only going to update 24% of the weights in this model. So now we'll move on to data setup. This is an English data set. I don't think it's the best choice for fine-tuning, but it's a simple set. You can find data sets on Hugging Face. Just look up data sets here. But we'll go ahead with this. We're going to load these samples. Should be fairly quick. It's just text data. And now we'll move on to training. So for this, we're going to set a pad token. So the way training works is you have these sequences of data, but the data sequences may not be exactly the same length. I mean, we can just go in here. Let's just grab this and have a look. So here we have so here we have the English quotes. So here's an example. We have a quote and we have a tag. So, yep, we have a quote and we have an author. And let's see how this data is being assembled. So going back to the fine tuning, it looks like we're just fine tuning on the quotes actually. So we're just taking the quote variable, which is here, and the quotes are not all the same length. So that's why you need to pad them to all be the same length to fit inside a matrix. And that's why we set a padding token. The padding token for Llama is, it's actually the end of sequence token is this one here. So that's what's going to be used as well for padding. Potentially that can create some issues, but it's quite detailed. We'll get into that in the advanced training. And then we set up the trainer. We're just going to run this for 10 steps. And let's see how that goes. So it's going to take 10 quotes and it's going to run through each quote. And what the model does is every time it feeds in the quote, it predicts the output. It then compares the predicted output to the actual output. So it'll predict each of the next words, compare that to the actual next word, and it will compare that. And the difference will result in a loss. So if the predictions are very different from the actual next word, then you'll have a higher training loss. And that loss then is used to back propagate. So that loss is used to update the weights by flowing backwards through the neural network. So you generate the prediction, you get the loss, and using the loss, you then use that loss to update all of the weights. And currently, because we've set gradient accumulation steps to 4, actually what's happening is we're calculating the loss 4 times, and then we're using those losses to back propagate effectively in one go every 4 times. So you can see the loss is kind of declining as we go along. And I'm not expecting it to change the output much here. I will show you in the advanced example how it does. But let's just move ahead and let's do inference. Inference is where we actually do some prediction. So here I'm going to just get it to stream very brief comparison. And this is some code I copied over. So actually this here needs to be to put a 0 because we want to move to the tens, move to the GPU. And my syntax is not exactly right. Let's go back and get the exact syntax. actually, I think I need to go to notebook. So I'm going to go to the Jupyter Llama notebook where I do inference. And here I actually have a script that that does all of this. So the problem, if you remember here, is that the runtime flag was undefined. So I'm just going to define that runtime flag. And now we will stream. And we do need to install the text streamer. This here needs to be installed. All right. So we do have this warning here. Actually, there's a small script that I should run before calling inference, which we can just run here. So if we want to clean that up. But anyway, you can see that the output is showing right here. I'll just stop that because I want to clean that up. So let's just clean up. All right, and here this is worth looking at because you get familiar with the structure, but for Llama, the structure is you have a system prompt that's wrapped within sys. Then you have both the system and the first user prompt are wrapped within inst, which is short for instruction. And then finally, you have this S token, which is a beginning of sequence. This should wrap both the system and the user and the assistant's response. And you can see that the end of sequence tokens is right here. So there we go. We've now trained and fine-tuned and run inference on this model. And I'll just show you now, if you wanted to push this model to the hub, you can run this cell. This is going to put it up as a repo onto your own organization. You can see Trellis is here. It's not going to let you push to Trellis because you need to be logged in with the notebook and have permissions. But you can swap Trellis to whatever your organization name is. And here what's happening is it's saving the adapter model. The adapter model is basically the deviation of the fine-tuned model from the original model. So we'll save that deviation. Then we're going to define a name and a target for the new model. Here we'll save the model. So this is saving, basically pushing the adapter onto the hub. So you'll have a new repo for the adapter weights, which is again the difference between the original model and the fine-tuned model. And then what you'll do is reload the base model. You'll apply the adapters. So that's the merge and unload. So reload the base model, load the adapter model, basically scrunch those two together, and then push the full model back up onto the hub. So that's handy if you want in future to inference the full model. Now, the last step here is you might want to push the tokenizer as well so that you have a tokenizer available in your repo. It'll just copy the tokenizer that was from the base model. Now, I think I just need to fix base model name. That looks good. This is actually not base model, it's model ID in this notebook. And here you can control the shard size. So it's going to split up the weights in your model. Usually I go for maybe 5. You could go for 10. Wouldn't recommend going higher than that. The advantage to 5 is that it can make it easier to load into Google Colab notebooks. So that's pretty much an overview of, from start to finish, of a simple fine-tune and allowing you to push it to the hub. What we'll do now is move on to the advanced fine-tune. Now, the advanced fine-tune notebook is available if you'd like to support this channel. It's available for $14.99 and allows you to do some more advanced kind of finicky things around the fine-tune that should help performance for small data sets. Now, to explain the benefits here, I need to go through 2 different concepts. The first is attention, and the second is loss masking. So attention is the idea that the prediction of the next token depends on earlier tokens. So as an example, if I say the quick brown fox jumped, something like this, and if we break that into tokens, let's just say for argument's sake, it's something like this, which this is not exactly how it would be tokenized because the tokenizer uses subwords. For argument's sake, let's say it's like this. So here we have 5 tokens, and we're trying to predict this 6th token here. And attention basically says whether you're going to consider the fact that the previous tokens were there in evaluating the next token. So for example, if you wanted to pay attention to all of these tokens, then you might have an attention mask that looks something like this. So let's say something like this. Sorry, I don't mean to put the dots there. Those. Yeah. So here's an attention mask where when we're predicting that next token, we're considering all of the previous tokens. So the attention mask is just a mask of ones. Now, I mentioned earlier that when you're training, you have many snippets, say quotes, and those quotes may not be the same length. And so you pad them. And padding means that you put in pad tokens. Actually, in the example I'll show you right now, the advanced example, we're going to put in pad tokens like this. So let's say that let's just say we have 1 padding token because the length of every sequence we use for training, instead of it being 5, let's just say that the maximum sequence length we're training with is 6. So we need to pad every sequence to be 6 long. Now for the attention mask, we don't want to pay any attention to the pad token because that shouldn't influence our prediction of this next token here. So when it comes to the attention mask, we put a 0 there so that any influence, any matrices that are going to take into account previous tokens, that entry will just be multiplied by 0 for the pad token. So there's basically not going to be any effect of the pad token when it comes to attention. So the idea with an attention mask is that you want to set it so that you ignore the pad tokens, but you do want to pay attention to all of the other tokens. And that's pretty much attention. And I'll show you in the example how we are going to tailor the attention mask to do exactly that. Now, the next thing is loss masking. And the idea here is selecting what tokens generated to penalize. Well, it's really more like what token predictions to penalize. So here again, let's take our example. Let's say we have inputs here of the quick brown fox jumped. And let's just say that we have outputs. And outputs are going to be predictions. So what we're going to do here is we'll make up some predictions. So after the word the, we'll just say that the guess is maybe boy. And after the word quick, we'll say the word is brown. And let's just say that it gets all the rest of it correct. And here we would have okay. So that's the inputs, that's the output, which I'll just clarify by calling prediction. And then the actual, of course, will just be a copy of the inputs. So the actual, what the prediction should be, is just a copy of the inputs. But of course, the outputs, the actual outputs are going to be shifted by 1 because the prediction after that is quick, prediction after quick is brown. So, and here, for example. All right, so what happens here when calculating the loss is the model will give the predictions and we'll compare them to the actual. And I'm just going to make up the losses here. But here, let's just say there's a loss of 0.5 because it thinks that it's boy, but it's actually quick. On the next one, the loss is going to be calculated as 0, let's say. On the next one, let's say the loss is 0. On Fox, let's say the loss is 0.1. And let's say here that it's 0. Now, just a small point here, which is here, clearly the model gets the token right. It guesses jumped and the actual is jumped. But there still can be a loss because, for example, jumped might be predicted with a probability of 90%. So if the model doesn't predict it with 100% certainty, then there's still going to be some loss because the model is not fully sure that it's jumped. So, for example, the only way you would really get zeros for the losses is if the model guesses the next token is 100% going to be brown, and it actually is brown. So very rarely will you see losses of 0. You pretty much see, maybe small losses. And then when it gets the token wrong, it generally will get some bigger loss here. And so here, what you can see is we've got losses for each of the predictions, and then these losses are then they're basically averaged across the tokens effectively, and that average loss then is used to back propagate through the network. Now that was a bit of a roundabout way, but needed to be gone through because now we get to the loss mask. So the loss mask determines which tokens to include in the loss calculation. Now, going back again, and let's take our inputs here. Just like for the attention mask, if we have a pad token, say that we have a pad token like this here, we actually don't want to include that in the losses. So any pad token that we have, we're just going to multiply by 0. But we do want to include all of the other tokens. So here we're going to put in loss masks of 1. Now, this doesn't mean that the losses are going to be 1, but what it means is that any of these loss numbers here, we're going to multiply by, here by the loss mask. So to make this more concrete, if we do have, say, a pad token here, and let's say the model predicts the output after a pad token is the actual token that comes after pad. Well, in fact, let's just say that the model guesses hello. The actual token is the. Lay out a bit neater. So now when we calculate the loss, obviously the word the actual is not it's not the same as high, so there's going to be some high value of loss here. Let's just say 4. But what we're going to do is multiply the loss mask by the losses. And what that's going to result in is that first loss, even though it's a loss of 4, we don't really care about it, so it'll be multiplied by 0. Whereas this next loss, we do care about it, so it'll be 5. The next loss will be 0.01. Next loss will be 0.02, 0.1, and 0.3. And so that's the loss mask. Effectively, it's allowing us to ignore certain tokens that we don't care about and that we don't want to penalize the model based on. Now, where this becomes particularly important is when you have an example of text. Now let's just go back and take an example here from this model. We go to the inference. So here, let's just take all of this and copy it across. Sorry. It's not allowing me to do a nice layout here. So let's just put in some more text like this. All right, so here we have some text. It's doing some weird formatting on me. That's fine. Who cares? But here we basically have a system message, and then we have this user instruction, and then we're starting off with the assistant response. And when we feed in some kind of prompt like this, basically what we want is we want to pay attention. We want to pay attention to all of these tokens here. So we want the attention mask to be all ones here. Although if there's any padding tokens before, we want it to be 0. But for the loss mask, sometimes it might be good to penalize the model based on predicting the next words here. It's just kind of generic information. But usually we want to penalize the model specifically based on the answer. We're not trying to train the model on predicting the next word in a question. We're trying to predict its ability, or rather a question here, or request. We're trying to train it specifically on the output. And what we're going to see if we're trying to train the model to provide a function as a response. So let's just say it needs to provide a function call, something like this. We are definitely going to want it to be graded based on this object here. We don't want it to be graded based on this question. And by applying a loss mask so that you target this point here for the losses, you're able to focus the model's training just on the answer. And that's going to be more specific than training the model on some kind of generic prediction of the next word in a question, which is probably something the model is already well trained on. Okay, so with that advanced fine-tuning as background, we'll move over to the advanced spreadsheet here. Now I'm going to just shut down the runtime for the basic spreadsheet, and we're going to get it set up here with our login to Hugging Face. You can see that we're being allocated some bandwidth from Google, and it will then ask me to log into Hugging Face. So you'll notice I run this cell first before running any of the other cells, because if you don't run this cell first and wait, what happens is the notebook will start evaluating the rest, and you'll never have you'll never be approved as login, and that will cause bugs and it'll cause it to crash later on. Okay, so one more step here. This is optional. You can comment this out, but I typically will connect by Google Drive. What this does is it means the model will be downloaded. In fact, I've already downloaded the model to my Google Drive. And the benefit of this is it means the model is going to be more quick to load. So I'll probably save maybe 3 or 4 minutes because of connecting Google Drive. All right, here we're going to load the meta model. Again, I needed to be logged in. In order to do that, I needed to be logged into Hugging Face, which I've done, so that should be good. So the drive mounting, I need to approve. And then it will load the model, and then it will connect Google Drive as the caching directory. And then we'll move on to installation of these packages. And Then we'll move on to importing those installed packages. And then we'll move on to loading the model itself, which I will get kick-started. I've separated it out here, the loading of the tokenizer. So notice that we'll see this printout later when it comes to it. I'm using a fast tokenizer. I'm setting the padding to be to the left-hand side. So that means each of my sequences for training, they've got the padding tokens on the left. And I'm also going to set the pad token to being pad. So I'm basically defining a pad token here. This means it's not going to be confused with the end of sequence token that we used in the basic notebook. And when I define that, I need to also increase the number of embeddings to match that length, because I've added one more token. And I'm just doing a check here that the model's pad token and the tokenizer's pad token have been set. So that should all run. We're just installing still up here. Let's get these tokenizers rolling. Let's get the pad token. Now here we have a sample string. I will run this just because I want you to see how inst gets tokenized. It's probably not a great choice of a token to or of a delimiter, because inst actually gets broken into multiple tokens and it does so in inconsistent ways. So wouldn't be my preferred choice, but that's the standard Llama choice. Then, like the basic model, we'll set up LoRa. This is very much the same as what we saw before. There's no real difference here. You can see I have the same target modules as in the base example. And you see the model is not being downloaded because it's in my Google Drive. So instead we're downloading these checkpoint shards, which takes about a minute and a half. Things will move very fast after that. So yeah, let's just talk about the data set here. So we'll install data sets, and we're going to use the function calling extended data set, which is for training models on function calling. Here we have the data set, and just to show you an example, just as an example here, we provide some context in the system prompt telling the language model that they can make use of certain functions. Then we ask the model to search Bing for instructions to fly a kite, and then we respond in a structured format. And the structured format allows a coder to take out the search parameters and actually do a Bing search and then return that information back to the model. Notice also that there's some training data here that doesn't call a function, because you don't want to condition the model to call a function every single time, no matter what. So you need to include some questions where the functions are available, but it's a question that doesn't need a function call, like this one here about watermelon seeds. And yeah, this is a a data set that's been developed by Trellis that you can purchase and request access. I think it's 10 euro if you're interested in function calling. All right, so I'm not a robot. By now we should have, the model should be loaded anytime. It's actually taking a bit longer than I expect here. Let's check Llama 7B. I'll print that text data set. So here what I'm doing is back to our loss mass discussion, and what this allows for is, just 1 second. Okay, so here we have just completed running, so the model is loaded, which is good. And you can see here initially the end of sequence token is this /s. There is no pad token set by default on Llama. So we set the pad token, and the pad token ID is 32,000. Here's the configuration of the Llama model. And then we have a sample string, and I said I'd show you how inst gets tokenized. It actually gets broken up into 3 different pieces. But you can see here we tokenize, we untokenize, come back to the same thing. And we've done the LoRa setup. So LoRa is now set up, and there are going to be 0.5% of the parameters will be trainable. So a pretty small amount. Now we will install the datasets, which I've gone through. There are 78 training datasets, and there's 21 test datasets. So now is the part here where basically put the training data together. Here what's happening is I've got the inputs, and then the labels are actually the actual outputs. So think of the labels as what the model should be predicting. And quite simply, the labels are the inputs, but shifted one to the left. And that's because basically the answer for predicting a given token's next token is always the next token in that array. So you just copy the array, you clone it, and then you shift it to the left. And here I've put an end of sequence token in the very last position of the predictions. So there's going to be a /s, and that predicts the end of the sequence. This is important because we want the model, when it responds with a function call, to include an end of sequence token. We don't want it to continue blabbing on. We want it to know that once the JSON object is provided, that's the end, and it needs to signal that by adding in an end of sequence token. And it's going to be important that we have a 1 there in the loss mask, so that we're actually considering the loss from predicting that end of sequence token. In fact, that's what we're doing right here. You can see we're setting a loss mask so that it matches basically the inputs minus the response. That's the starting index. So if you have your full sequence input and response, we want to have 1s for all of the response. So we have 1s for all of the response, and we will have a 1 as well for that last position. This is the shifted loss mask. Basically, it needs to match that response. So the labels are shifted 1 left, so the loss mask also needs to be shifted 1 left. And then we need to add in a 1 to match up with that end of sequence token. And we'll see this. So I think now we have run that. We've run that. We'll prepare the data set. So we're now putting this all together in the format we need. We'll apply that setup to the 2 training sets. Well, sorry, to the training set and the test set. Now we'll take a look at some of the data set. So you can see here right at the start, it's just padding tokens because we're padding all the sequences to the same length. So that makes sense. Notice how the attention mask is 0s because we don't want to pay attention to those padding tokens, and we don't want to include the loss. So that's why we have 0s there. Now at the end of the sample, we have attention mass of 1 because we do want to pay attention to the previous tokens. But notice here how the loss mask is still 0, and that's because we're still in the question portion. And what we want to do is we want to focus the model, and we want to focus the training on the answer part. So there's actually only 7 tokens that we're focusing the training on when it comes to looking at losses, and it's the last 7 tokens. And those last 7 tokens are the finish token, and then we have apples are nutritious. So these are the 7 tokens, and we're focusing the loss. We're only considering the loss from these 7 tokens. And notice how we are including the end token, because that's important. As I said, we don't want the model to ramble on afterwards, particularly when this here is a JSON response. All right, so now we're going to just generate one sample. This is of the untrained model. So you can see here, we have the system input, your helpful research assistant. We've provided two functions here. There's a list files function and a save chat function. And then we give the instructions for how the language model would call a function. Now, you can see here, the question is, what are my files? So what the model should do is recommend list files. And that's what the correct assistant response is. It says list files. But what you can see here that actually the assistant is providing, you know, it's kind of a reasonable response here, but it's then blabbing on further with other stuff. So this is going to be a harder answer to, and this also doesn't make sense because it can't actually retrieve the files, and then it makes up the file names. So you can see the generated response is not quite right, and that's why we want to train it to give a more terse answer like this. And just notice we're generating a sample. This is sample 0 in the test data set, which we will also run later on. All right, so let's go to training. We've got a training script here. And we have a custom data collator. Basically, I am putting the data together in a more manual way than automated. And the reason for that is because I want to apply the loss mask. In particular, I want to make sure that the loss mask is being multiplied by the actual losses so that we focus on those response answers. So this is the custom compute loss function. So we're computing, we're calculating the outputs in a forward pass. We're calculating the logits, which are a representation of the probabilities of each of the 32,000 tokens in the vocabulary. So there's a probability for each possible vocabulary as the next token. And what we're doing down here later is calculating the losses by comparing the actual to the predicted. And this is the key step here where I'm applying the masked loss. So yeah, I'm basically applying that the loss mask so that we only focus on the response. Okay, sorry, I've run that already, it doesn't matter. And let's train. So you can see here, I've got a table printing. Like here is an input token, a predicted token, and then a true token. And the loss is achieved by comparing the predicted to the true. Now notice how we have the loss mask and we have the raw loss, and then we have the masked loss. So there's a raw loss pretty much for every token, but when you apply the loss mask, it results in the masked loss being 0. So basically all of the loss, the masked loss should be 0 until we get to the start of the prompt. And the very start of the prompt, here it's a function call. You can see you have the instruction, you have 2 carriage returns, and then this is where the actual response starts. In this case, the model is predicting, it's predicting a function call, but the actual correct answer is to answer the question about the origin of fortune cookies. So you can see the model is not getting this training step correct, but we are correctly applying a loss, and it's getting a big penalty here because it's incorrectly predicting how to respond. It shouldn't be responding with a function, it is, so it's getting a big loss. Now notice how it is predicting a lot of later tokens correctly, and that's why it's getting smaller losses here. Okay, so training is underway. You can see here it looks like in some of these training steps we have some errors. Basically, sometimes the model during training can run into bumps where it gets into a state, makes it hard to get out of. And we shall see if we remain in that state. Just a reminder of the configuration here. So we're using a batch size of 2. That means there are 2 data sets going in at a time. And gradient accumulation means we're saving up for 2 steps. We're saving up what the loss is effectively. It's technically the gradients, but so let's have a look here, see if we're having issues with the training still. It's not looking great. So I'm going to stop the training. All right, so I've rerun the training here. I basically, I made sure that the model was downloaded fresh from the Meta repo. So I wasn't loading from Google Drive. I have noticed in the past that can cause issues. I reran the exact same training and here with 2 for gradient accumulation and 2 for per device train. So I've about 40 or actually 38 steps. And you can see here that every training step is giving a reasonable loss. And the loss is arguably dropping a little bit as we go through the steps here. So let's take a look at running another sample and see if we get any better results than the last time. And in fact, I'm not going to be able to see that result because I'm currently pushing that model to the hub. Okay, so I am going to now run some inference on our trained model using this script here. I'll provide a link to it in the video. So I've run the setup and install. I'll be running on GPU. And now you can see that I'm actually calling the trellis model on the hub, which is the model that we just pushed. I've not mounted Google Drive. I've got the model loaded, tokenizer set up, and we're ready for inference. I've run a first inference here asking about the comparison between Sals and Bachata. It was very long. But yeah, that functioned as expected. So now what we want to do is test some of the prompts that we had previously tried and see if we can do better. So let's go back and find the pre-training result and see if we can perform better than that. So what I'm going to do is copy all of this here. And we want to see if we can perform better. The assistant was a bit verbose. We want to see if we're going to perform any better. So let's just say prompt equals I may need to stringify this prompt first. So let's do that. Okay, so I've just pasted in this instructions variable. It's really a prompt, so I'll just call it prompt. And then we're going to stream with that prompt as the input. So let's see what happens. Oh. Yeah, it's like double wrapped, so that doesn't make sense. That doesn't make sense. It actually worked, but I don't need to include I actually just want to set that as the whole input. So I'm going to just copy this function and make a new version. Here, what I'm going to do is get rid of this and simply set prompt to user prompt. This. Now when I run this here, we've now got that working. So now we're saying to call a function, respond immediately and only with an object in the following format. And you can see the response here is exactly what it should be from the generation. It's even got these brackets correct. So that's good news. You can see it's matching here, list files. And it's a lot better than what it was pre-training. Let's try another example. I think there may be an example. Let's just modify this and say, instead of what are my files, let's ask a question from the function calling repo. Let's try to find the function calling repo. Find it here. And here, let's just find some question that does not have a function as the response. So maybe something like this. Now we actually do need to pick something from the test data set, because if we pick it from training, it will be not very impressive. So let's try this one. Did humans really land on the moon? And notice how when I put this in, I'm going to keep the definition of the functions, because I want to test it and push it so that what we don't want is for it to respond with a function just because it's provided the option of calling functions. So let us now see if this works. So did humans really land on the moon? The moon landing in 1969. Interesting. Did humans really land on the moon in 1969? And the inst is that. Interesting. So in this case here, I'm maybe a bit surprised. That it didn't give a more comprehensive answer, but at least it's not providing a function call, so it is coherent with another slight variation here. Yeah. So yeah, this is looking reasonable. You can see that it's correctly not calling a function in this case. And this is only a 7 billion model, so it's pretty impressive that this is working quite well for such a small model. I'm just going to delete this here because we have of course no need for this normally. I'm just going to put back in what we had in the original. Also, there's no need for that. And let's just get it back to generating some reasonable response. Okay, so it's funny you put in nobody knows the difference between, but it's actually possible. Yeah. Yeah, it's giving us the answer here. So this is pretty much a summary. We've gone through a lot of steps and found a lot of different interesting issues along the way. I will share a link to the kind of lecture notes here, and I'll share a copy of the free notebook. I'll give you a link for if you want to support the channel and buy the advanced fine-tuning notebook. I'll also provide a link to the function calling extended dataset and to some of the models which you can download, already trained the 7 billion function calling dataset. And the link there, you'll find the inference. So I hope this was of some use, folks. Please let me know in the comments with any questions or requests for other videos that you might like to see, or any bugs that you might find. Cheers.